right, gang, methods of reduction, Mass 6620, spring 2015. A couple of things. Exams and homework. There's a delay on getting those things graded because I don't have them. They're in my office at school, and I'd say I probably have, I don't know, maybe half the exams graded. I haven't even touched the homework. Uh, with all the snow recently, I graded these in my office, and I thought that I think I graded them on Wednesday, and I thought, well, I'll come back in on Friday and get, just finish up the grading, and and actually I left out Wednesday night not thinking in a hurry because I knew that there was weather coming. Not even putting two and two together, the weather coming, chances are I wouldn't be back on campus on Friday. So anyway, guys, long story short, I didn't get back to campus on Friday as intended. So your your exams and homework are sitting in my office. I won't be back on campus until next Monday because this week that I'm actually putting this video up, by the way, for the third time. Uh, do you detect the sense of pissed offness? Uh, but anyway, for the third time, putting this up. But anyway, guys, I'll be back in my office Monday. I think that's the 16th, and I'll get these things graded as quickly as possible and get those back to you. So please accept my apologies on the delay on this, but just didn't know we were going to get 17 inches of snow in Kentucky in March, or any month for that matter. Number two, change of plans. I think in a previous video I told you that what I wanted to do next was get into the mathematics of logistic regression. I was really looking forward to that because it's kind of cool to show how the maximum likelihood estimation process leads into what we use to set up an iterative process. It's a manipulation of matrices just like we use with simple and multiple regression, except there's not a closed form solution. We have to create an iteration to come up with the regression coefficients. So I was really looking forward to teaching that, and I was all pumped up, and I sat down and thought, let's look at a plan for the rest of the semester. And I keep forgetting this is a 2-hour course, and I only have essentially 7 weeks of class left to go over test theory. So guys, I had to regroup. And for those of you who are teachers, you understand that sometimes you have to do that. So in an attempt to set a foundation for something I want to do in what we call test reliability and validity, test theory measurement and so on, which I'll start probably next week or the week after, I need to I need to get busy. We need to get into to something else to set the framework for that. So, guys, anyway, what we're going to do in this video, this is going to be a PowerPoint video, and then I'm going to branch off into some different things. What we're going to do here, we're going to look at what we call methods of reduction, and I'll explain it to you throughout. Okay, so let's just go for it. Example number one. Let's say, and I'm going to motivate this to an example, and then we'll get into the terminology, and then I've got some pretty cool little video and even a simulation that I want to look at. But if we were to give these questions, for example, to a group of students, like for number one, in general, how would you say your health is? And let's just assume that these things are measured on a Likert scale. So from 1 to 7, 1 is just feel absolutely horrible. My health is horrible. To 7, I'm ready to run a marathon. Felt fit and well. Scrolling down, I see of loneliness. Are you lonely? Do you have enough money to do the things? So on and so forth. So we get all these responses. Now, just simple observation. We can look at these, but we can't see the inner working relationship between these. For example, is there any relationship between students, for example, who feel lonely and feel sad and are happy at school and so on and so forth? So What could possibly be done to this is called reduction analysis. And we can do these things called, which I'm going to introduce here in just a second, called factor analysis and principal component analysis, which allows us to reduce these observed variables down into what we call components and factors. Now, so what happened here is you can see at the over to the right, you'll see the general health, fit and well, physically active, run well, energy, all seem to load on what we might call as a factor physical well-being. The second group, life enjoyable, good mood, fun, sad, lonely, so on and so forth, might be more expressed as a psychological well-being. Now, the numbers that you see there, starting with the 0.61, the 0.75, the 0.71, the 0.62, and so on and so forth, those are the correlations between that test question and this overall explanation of this group of test questions. And then the numbers you see over to the left, the 0.75, 0.77, those are the correlations between the broader explanation of the responses. So you can see what happens is we get a large group of test items, or really whatever, but we're going to focus on test items. And we want to be able to reduce these in to a more of a latent trait that can be explained by kind of a more kind of a broader title. Okay. Now I tell you, first time I saw this, I didn't know when I was going to tell you this, but I'll tell it to you now. First time I saw this was in graduate school, and I took a class just on factor analysis and principal component analysis. You guys are going to get this in about 2 weeks. I took 16 weeks of it. And I was really skeptical at first about this whole factor analysis, principal component analysis, because there are limitations. And there are kind of moments of raising your brow and questioning some of this stuff. And I'll point all that out. But there's also, the process itself and the ability to manipulate and organize, enormous masses of information is pretty much priceless. So I decided, being the geek that I am, I decided I was going to take it, and let me back up. At this time, I was developmental coordinator, coordinator of the developmental math sequence. So one semester, we had a large group of students take a multiple choice exam for math. At that time, it was 101 because at that time we were on quarters. So I had we had these things on Scantron, so it was really easy. It was easy for me to tabulate the responses and actually run a factor analysis on the 25 questions on the exam. So question 1 was factor this. Question 2, what's the area of this triangle? Question 3, so on and so forth. I was amazed to find out that from the test that we were that I administered from the textbook, we covered 5 chapters. Of the 25 questions, and these things were not in order; they were scattered throughout the test. Of the 25 questions that came from chapter 1, all of those questions loaded on, after I did this reduction analysis, loaded on that particular factor. All the questions that were representative of the objectives from question 2, except 1, loaded on the factor that kind of combined all those responses as being similar responses. So this is something that we're going to end up doing ultimately. But guys, this is it's kind of cool stuff, and it really sets the foundation for some of the stuff that we're going to do in test theory. Example number 2, let's say a director of a graduate program, i.e. me, would like to use a set of student characteristics to predict course success, or program success. This gets into terminology on what we call observed and latent variables. Observed variables, I think I just knocked out my microphone, but I didn't. Observed variables are things that we can actually ask subjects and we will get a response. For example, GPA in college, GRE score. GPA may have been 3.2, the GRE may have been 1,400, number of hours of volunteer service per week, 22, and so on and so forth. Latent variables are things that aren't directly observable in terms of asking a question that we can get a response. These things are visually observable, but not statistically observable. In other words, we don't have an observed variable that we can just say, hey, what's your personality type? We can't do that for these things that we call underlying constructs. We have to use a more clever approach and ask a sequence of questions to tie in to some level of personality, motivation, intellect, drive, these different things that we do a lot in education research. Example number 3. If we're running a multiple regression model and we find out that we have some of our predictors that are highly correlated, this runs into what we call multicollinearity issues, something that you'll learn a lot more in 6500. For example, some personality measures may highly correlate with some measures of motivation and academic history, possibly. Intellectual ability may highly correlate with some other measures of the similar components. Now, what do you do when that happens? How do you handle multicollinearity? Because that can completely drive your models insane. Some solutions are just eliminate the predictors that are highly correlated. Well, the problem with that, you're going to explain less variance in your model. Second thing, you could create composite scores. Composite scores are just where you add scores together. So if you have two things that are highly correlated, you may add them together. Again, you're eliminating one of the predictors, and you're still going to lead to explaining less variance in the dependent variable. Final solution, which makes a lot more sense because it explains more variance, is to create what we call principal component scores and carry out the principal component analysis and factor analysis that I'm going to teach you more in this video and in the next one. Oh, I meant to do this. I was going to be really clever and just click my pen the whole time, but I won't do that. Another thing, example 4, this will be the last example, in test construction. If you think about it, in high schools and colleges, we're really not held under much standard, or at least I don't think most people are, in creating their in-class test. We pretty much do the best job that we can. We may have, if we're part of a promotion tenure plan, we may have someone that takes a look at those kinds of things. But at the end of the day, I know for me, when I prepare an in-class exam, I prepare it and I go with it. Well, guys, that's not always the best way, especially if you're creating a test that has higher consequences in terms of maybe selection to programs, graduation, and so on and so forth. So, guys, when we develop tests that really have important consequences, we run into things that are called reliability and validity issues that have to be addressed. And just to kind of run through a way that this factor analysis, principal component analysis thing could really help us is we could, first of all, begin with a very large number of items if we're actually trying to measure some sort of math knowledge, reflecting a best guess of arithmetic, pre-algebra, college algebra, geometry, trig, and calculus. What we would do from there is we would derive these factors and we would see what questions loaded on what components and ultimately what factors. This probably doesn't mean much just yet, but trust me, it will. What we could do is we could add or delete questions, most likely delete questions, give our test to another group of students, and continue this process until we have several factors that represent the areas that we want to be measured. Okay. Reduction methods. What do we have here? There are two reduction methods that I'm going to teach you. One is called principal component analysis. These things create components, and factor analysis is a process that creates factors. Keep in mind that both of these are data reduction methods. In other words, data reduction methods happen when we have an enormous set of items, potentially test questions, and we want to look at these underlying relationships between, people who answered maybe 1, 3, 5, 7, whatever it may be, correctly. Are there correlations between pairs or even sets of questions? The first thing, what's a factor? A factor can be thought of something that's not directly measurable, but something that's similar in a pattern of responses of the observed variables. Now, guys, when I talk about observed variables, when we look at a standard data set, which we've set up 1,000,000 times, well, maybe not 1,000,000, but we've set up a few times, where on the columns you have your variable names, and the rows actually turn out to be your subjects. Well, when I talk about an observed variable, I'm talking about a variable that we actually include in a data set. So under the second bullet, things that we could ask would be income, education, and occupation. Income, someone makes 80,000. Education, they have a master's, and their occupation, they're an attorney, engineer, whatever it may be. Something we may derive from that, which is called a latent variable or a factor, is something called socioeconomic status. It's not directly measurable, but something that may be inferred from the combination of income, education, and occupation. So what's a component? Guys, later on in the video, after I get out of this PowerPoint, I'm going to illustrate a visual of components, what we call principal components. But in the meantime, principal component analysis seeks to reduce the number of variables into a smaller set of components. And actually, it starts out whatever number of variables that we have, we create in the first phase the same number of components. And then we find out that some of these components are really containing a lot of variation, and some of these components really don't contain much variation. They don't explain much variation, and we end up getting rid of those. But in the beginning, whatever number of observed variables we have will create the same number of components. Second bullet, PCA analyzes the variance in the variables and reorganizes into a set of components. We use something called a orthogonal rotation to make that happen. And well, as I just said, I didn't know that bullet was down there. An initial set of components equal to the original number of variables. Guys, factor analysis breaks into two types of factor analysis. One is exploratory factor analysis, and this just tends to summarize our data. And it looks at highly correlated variables and group them together. Confirmatory factor analysis is far more sophisticated. We're not going to get into that in this class, but this is just allows us to test a theory about potential underlying factors. Exploratory factor analysis, again, will be our focus. It's a reduction technique that looks at the structure of a set of variables, and it hypothesizes an underlying construct. So an underlying construct, a construct is something like, motivation, attitude, socioeconomic status, something that you can't directly observe, but you can put all of these observed component or observed variables together to create kind of a collaborative approach at measuring a particular construct. Guys, limitations, and there's tons of limitations here. First of all, there's no way to test your solution. There's an infinite number of rotations, so the final decision really depends on the researcher's interpretation. The third bullet I ran into not long ago, well, actually, I say not long ago, it's about 10 years ago. Sometimes people have research projects and they really don't know what to do with it, and they just start throwing some factor analysis together and try to get a publication. Keeping that in combination with bullet number 4, sample sizes need to be pretty large. I'll get into that more because this process is extremely unreliable with small data sets. which is kind of weird because I'm going to first of all illustrate it with some small data sets, but we'll keep that in mind. As far as a last-ditch effort in some research projects, a really good friend of mine, when she was finishing her PhD, she had a data set that was kind of cool. She got into to looking at how self-efficacy and beliefs about learning and so on and so forth impact success in a classroom. And she really wasn't finding much, so someone told her that she should maybe look at some principal component analysis, some factor analysis, and her doctoral advisor didn't know much about statistics apparently, and he let her get away with it. Well, anyway, when she finished her dissertation, she had something that got her. Actually, she didn't get a PhD. She got an EDD, but she got her doctorate. But she had something that clearly wasn't publishable in any research journal. So, guys, it's often used as just kind of a last-ditch effort, but it's far bigger than that. Principal component analysis. Again, it's a large sample procedure. I think this girl had 65 subjects, so it was very, very poorly designed for her data set. I think 500 to 1,000 is what you typically need for a principal component analysis. But I've seen some really cool stuff done with 250 to 300. Variable reduction technique and used when variables are highly correlated. Again, that can be issues if we're trying to use highly correlated variables in multiple regression. Reduces the observed variables to a smaller number of components, and the smaller number of components account for most of the variance in the observed variables. It's kind of cool that you can sometimes, I've seen illustrations where we may have like 15 variables, and you run some factor analysis or principal component analysis, and you end up getting 15 components, but there's really just 2 of those that are explaining most of the variance in the observed variables. And you're going to get really, really pretty good at that before it's all said and done. So guys, again, summary, PCA, number of components equal the number of observed variables. The first component accounts for the most variance. The second component accounts for the second, and so on and so forth. The components are uncorrelated. And ultimately what we get into with the first component explaining the most variance, the second component accounting for the second most variance, and so on and so forth, we eventually get into components that are accounting for very, very trivial amounts of variance. So we can eliminate those and just focus on the components that are really explaining the significant amount of variance and focus on those. And guys, we get into eigenvalues and eigenvectors, which eigenvalues indicate the percentage of variance explained by each component. We'll actually create a standard deviation and, of course, square that to get into the variance explained by that component. So important terms, things we're going to get into. We're going to get into correlation matrix. We get into an observed correlation matrix. We're going to get into rotation. We'll focus on orthogonal rotations. These things just make solutions more interpretable and allow us to understand certain components that can be eliminated. Rotations used after PCA to maximize high correlations and minimize low correlations. Numerous methods. We'll focus on Varimax. And Varimax is just a variance maximizing procedure. Okay? And what you're ultimately looking at is we look at these perpendicular vectors and think about having a scatter plot just on X and Y. How can we take these perpendicular vectors and shift them around, rotate those around to where it explains the most variance in our data set? So kind of cool. Now, it's all about the base. I forgot this. It's really all about the variance, and this has nothing to do with factor analysis, but something that I think that you should kind of have on your in your repertoire, if you will. let's say that we were wanting to, we had 3 students in a class, and we have been assigned the task of determining which student is the best, which is the second best, and which is the third best. And we think, well, I tell you what, we're going to give a midterm, we're going to give a final. So student number 1 at the top got a 70 on the midterm, 81 on the final, got an 80 and an 80 and a 90 and a 79. You'll notice that the average over here, even though the final exam may be most weight, I'm sorry, not most weight, but maybe the most important. Student 1, student 2, student 3. Student 1 scored the highest on the final, but ranked the lowest because of the impact of the midterm. Student 3 scored the lowest on the final, but ranked the highest because of the midterm. Now, you might say, well, it's because of equal weighting, but it turns out that variance has a lot to do with ranking, even when the weighting of the final and midterm are completely different. For example, if you look at student 1 who scored 81 on the final and 65 on the midterm, even though that person scored the highest on the final with an 81, and that the final was 90% of the final grade, that student still scored lowest on the total average. And the reason is there's no variation in the final exam, or very limited variation in the final exam. Final exam scores only range from 79 to 81. So we have very, very limited variation. But even though the final attributes to 90% of the final grade, and the midterm only accounts for 10%, the added variation for student 1, student 2, student 3 scores on the midterm kind of overwhelms the ranking process. So, guys, it really is all about the variation. When we have a final exam, for example, like this, 81, 80, 79, that has very limited variability, even though it's weighted at 90%, it has very, very little impact in sorting through and arranging the ranking of the 3 students. Now, I want to get into something, taking a picture of a teapot. How can you rotate this thing to get the picture that gives you the most variation? So, guys, I'm going to shut up, and well, I don't know if this thing has audio or not. I actually forget. So let me play this. So how to take a picture to capture the most information about the teapot. Well, what you would want to do is you want to rotate it around, right? And if you look at the 3 bottoms, it has the thumbs down. It doesn't provide the most information. But if we rotate this around, we can ultimately get a picture of the teapot that has the largest surface area. So guys, as we rotate this thing around, we find that there is a first component, so finding the second longest axis, while fixing the first axis. So what he's attempting to do, I know it's a he, he's attempting to rotate that on the vertical axis to where it's the biggest, and then he comes in and assesses the variability from on the horizontal. So rotate the objects around its center to find the best orientation. First, find the axis so that the object has the largest extended average along the axis. Then rotate the object around the first axis to find the axis that's perpendicular, orthogonal to the first axis that has the largest extension and average along that axis. So the first and second axis are called the principal components. And sometimes, in fact, often, we can encounter situations where one axis explains much more variation than the other one, and we can eliminate one of the components and not lose much description of the variance in whatever we're taking, quote unquote, a picture of. All right. Now I want to get out of this, and there's a really kind of cool website here. John Calipari, that's kind of funny. That I think that I found, and explains principal component analysis visually. So for some reason this website is not wanting to react. All right, so if we come up to the 2D example right here, and what this allows me to do is it allows me to move these points around. And what will happen is as I move these things around, you can think of the red line as the one that is explaining the most variation. The orthogonal vector, perpendicular in 2 dimension, is the one that always explains the second amount of variation. Now, if you look at this first illustration, you can see that we're plotting our x's and y's. I'm sorry, we're plotting our points on an xy coordinate. But now, if we take a look at this red axis, which is principal component 1, and principal component 2, and rotate this, what we can see here is we can see that the variation across principal component 1 is more than the variation across principal component 2. So we would be able to drop principal component 2 and still explain the same amount of variation, or at least maximum variation of the way that these data points are actually presented. Now, guys, you got to think about this as a vector. So this vector, this red line, goes all the way across, and then we're looking at the variation of these points from that red line. If we look at our green, the variation goes actually left to right. So we're not getting much more explanation of the variation by including the green, because down here we can see that the higher variation is for principal component 1. Now, a 3D example kind of looks even better. So if you look at this line, right, this is the x, y, and z, and what it's done is it's come in and chosen the red vector as principal component 1, the blue vector is principal component 2, and the green vector is principal component 3. Now I can show the PCA by going a rotation. So what it's going to do, it's going to take that kind of the corner of a box, if you will, where those 3 vectors meet, and it's going to rotate those things to where it explains the most variation in the direction. And what you can see here is you can see that the green vector goes right through a cluster of points. The red vector goes through a huge cluster of points, but this blue vector out here is just kind of pointing out into space, right? So what we can see by the blue vector is the blue vector really isn't explaining much variation, and at the end of the day, the green vector isn't either. So we could probably take these 3 components, because we have 3 variables, and this variation here could probably be explained from 1 component and not 3 components. So in terms of, again, the reduction principles, the reduction motivation, we could very, very likely explain the variance in this model by 1 component and not 3 components. And this becomes very important once we find the number of components that explain maximum variation in our data. Then we can start to look for factors, these underlying latent variables that explain this accumulation or masses of observed variables. All right, gang, that's all I got. Next video we'll get into actually getting into R, and we'll actually get some hands-on data. We'll actually go and probably tinker around with some matrices too. So guys, all I got. Take care.